All right, while we get our next speaker, our first speaker, set up and ready to go, I just wanted to say, I neglected to say this morning, the team, and Chaz alluded to this, but the team that is running this workshop is amazing. And I really miss working with them because this is the team that I used to lead. And so, huge props to Elise and Tracy and Catherine. And then online we have Melanie and Megan and Frank. Right. Frank is outside at the registration tent. We have our IT helpers too, Pina and Wendy in the back, and Alex also in the back. And they really make this workshop, they and all the speakers, of course, make this workshop what it is. And yeah, and they're doing a great job. So anyway, okay. Are we ready to go?
Yes.
Okay. All right. So our first speaker is up on the screen. Hey Didier, how are you?
Hello, good morning.
Good morning. Good evening where you are. I'm going to read a quick introduction, and then if you want, I can interrupt you when you have 5 minutes left, or if you have a timer there, then I won't have to interrupt you. So it's your choice what you would like. Yeah, if you'd like.
Do what you prefer. I have a timer, but
Okay, I won't interrupt you unless you're going long. Let's do that.
Okay.
Okay, so Didier Queloz is a professor and head of the Center for Origin and Prevalence of Life at ETH Zurich. Didier shared the 2019 Nobel Prize for the 1995 discovery of the first giant planet orbiting a star outside of our solar system. The discovery of 51 Pegasi b through the radial velocity technique kicked off the modern field of exoplanets. Didier has spent the last 30 years working on many instruments and observing programs, leading to the detection of hundreds of planets, including many breakthrough results. He's currently leading the Terra hunting experiment, which will use the HARPS 3 spectrometer on the Isaac Newton telescope to collect data every night for at least 10 years on several dozen solar-type stars to search for planets with roughly the same mass and surface temperature as the Earth. We're very honored and appreciative of Didier making time in his very busy schedule to speak to us today. And given his extensive exoplanet career, it is very fitting that he is going to give us the opening talk of this 25th anniversary of the Sagan Summer Workshop series. And the talk is entitled From 51 Peg to 5,700 Exoplanets, 30 Years of Exoplanet Demographics. Take it away, Didier.
Thank you very much. So can you hear me? Okay, do you see my slide?
Yes.
Okay, so I have twisted the title because I think this title was way too mild compared to what's going on in the field right now. So I think we are experiencing a true revolution. So I want to go through that and maybe share with you some thoughts that would serve maybe as a trigger or maybe element that you will expand, I'm pretty sure, during this great meeting. I really apologize not to be with you. I would have loved to be, but it's just what made impossible. So I like to start with something obvious, but I would like you to reflect on something here, is on this. We all know very well what we're talking about here. This is how we detect planet by radial velocity or by transits. And I want just you to think about that a little bit and think about that most of the planet that we have detected so far, I didn't make the math, but maybe more than 95%, they have been detected by these techniques. I think what is brilliant in these techniques and what is also shocking is nobody would I bet on this at the beginning. The reason for that is because these techniques are really inefficient to detect planet. I think the radial velocity kind of gets something, but there's always ambiguity of the mass, and you take forever to get something like Jupiter. And the transit, it's so unlikely you get a transit when you consider the solar systems. So you have a couple of papers in the 90s that even specify that we should not spend any time doing this. Well, still, I think in the last 30 years, we have to consider that this is the most efficient technique so far, while I do believe this is just the beginning. So just to keep in mind this was how things started. Now, the second thought I would like to share with you is what has happened in 30 years is essentially driven by new instruments or innovations, because anything that we have done at the beginning was not planned. And we had to reinvent the wheel essentially on everything. Either do we use an equipment and you twist it to make it useful, or you just develop a new machine. And I would like to just give you this A nice example, it's easy. This is Elodie. This is the one that we've been using to detect the first planet. And the reason why I want to show you that is an example, and it could be applicable to many instruments that have been developed in the last 30 years. I think, why did we end up in this kind of machine, which is now a kind of a reference for the new generation? We are now starting the fourth generation of this machine to detect planet. It's because of a series of opportunistic moves. So it's all about opportunistic move, essentially. At that time, three elements came on the market. They were not existing before. The first one is optical fibers. We didn't have that before, or they were poorly efficient, so they started to get into the astronomy. The new gratings, the R4 grating, you see the piece here of this is the first ever R4 grating used for astronomical equipment. So any high resolution machine that have been detected planet have been using the same gratings from Richardson. It's going to change in the future, but for the last 30 years, the only thing you have here is 1/4 of the one you have for HARPS, and it's even a smaller version for the biggest spectrograph and bigger telescopes there. So it's because of this element plus a complete new generation of computer that made the discovery possible. So I would like you to reflect on that as well, to remember that whatever you do at some point, you will have to go back to the machinery which is doing it, and you have to look what is realistic. Now, my advice is don't expect this to be easy, because we build that on a shoestring. We essentially have almost no fundings to do that because nobody will fund that. That was a crazy development. So what I realized right now is when it's too easy to get the funding, you should be suspicious. So if you suffer to get your machine to build the new equipment, so it means you're on the good tracks, and that's what happened 30 years ago. So that would be my second thought here. In any technology we'll be talking during this meeting, bear in mind, at the end, it's about equipment, but about the right equipment and the right opportunistic equipment you have. Now, what's interesting to figure out is we have a beautiful theory for explaining the formation of planet, but it doesn't work so well. And the way to just remind you that is using this simple picture, which is the beta peak observed in the visible white light and in ALMA in a millimetric wavelength in the bottom. So I like showing this picture because it's very easy to understand. I think, well, the theory is beautiful, how challenging it is then to make a planet. So on the top, what you see is the reflections of all the solid material, which is very thin. By the way, you see the secondary disk, and you know there are planets being detected there. I don't need to mention that, but I just want to reflect on this, on the fact that the reason why you're building this planet is because this gravitations and the structure of this kind of system allow to have a very thin amount of material that keep gluing and eating to each other, that making the core material to build the planet there. So it's kind of a magical situation you have here when you make the planet, and it's all about building up the planet from that stage. And when you compare with a massive component you have, which is the gas component on the bottom, you have a complete different picture. Well, first, it's not that thin because of the hydrostatic equilibrium. So you have just the pressure that maintains the gas much more, I think, wider, elongated on the vertical axis. So it's not that easy to get the stuff together. And the most obvious element here on the picture is there is a moment when you don't have any more gas. There is a kind of a cutoff line here to come distance. And we know that corresponds to what we call the snow line, and you have that for all the gas. Now, what is beautiful here is when you put these two pieces together, there is a kind of clear understanding the amount of material you have, which is in solid form, is just massive beyond some distances. So the whole idea that you form planet very fast on giant planet on the outskirts of the solar system is all the story about the giant planet in the solar system. And it's all about the global picture that you expect most of the planetary system to look about the same because of this very reason when you form the planet there. Now, we know the story, we know exactly what happened. I think what I'm telling you is incomplete, and it is hugely incomplete. It's just not the detail, it's hugely incomplete because we know that practically there is a lot of planets that we're forming which are different from the solar system. And I used to call that the gift of the universe. The reason why it's a gift, because I think without all these planets, I will not be talking to you. I don't think this meeting would exist because we will be battling to find maybe a dozen of planets, barely, because that would I would have expected if we don't have all the other planets. So what we have is this beautiful I mean, populations of planets. This is every dot is discoveries, whether it's a transit of radial velocity here. So I only include radial velocity and transit. I don't want to add the other one. There is also some other planet, but they are marginally representative here compared to this one right now. Now, the reason why I love this diagram, because essentially all the planets you see on this diagram, they just don't exist on the solar system, kind of. I mean, either they're just too close, either they're just too big and too close, or even if they are into the Jupiter regime farther away, they are eccentric, or they are not only one Jupiter, but maybe 10 mass Jupiter, 5 mass Jupiter, they are the Mars orbit. There's all these kind of planets that we don't have in the solar system. So it's kind of a very fascinating situation we have here, because all these planets turned out to be extremely easy to detect with a very inefficient technique I described at the beginning, including radial velocity as well, and the transit more obviously there. Now, clearly, we know that as well, the solar system, at least the Earth and Venus, is completely isolated right now. We don't have any discoveries in that regime that is matching in terms of period and radius of mass. If you try to draw kind of schematically the distance where we kind of failing to detect any planet, you have this kind of bias or detection threshold. It's not strictly speaking a detection threshold, because actually you can cross it a little bit. It becomes more unlikely the more you go there. But clearly, the better you approach it from the left side, the more difficult it is to find planet. So what is beautiful here is essentially the radial velocity and the transit have detected planets that were not supposed to exist, according to theory. So the good news, if you're working on other technology like astrometry or microlensing or anything else, there is a complete territory here, which is in explore, again, because radial velocity and transit just doesn't work very well there. So the situation will be interesting to explore, because when you do the math right now, which is this diagram is very misleading, because there's a mixing of different surveys, different size, different technology here that's being used. But still, you can try to get some idea what is the likelihood that any of this kind of group, I call that group of planet, will be found on stars. If you take stars typically like the sun, this is kind of a number you find in literature. There is kind of a margin on this number, but it gives us kind of the ballpark figure of the chance to pick up a planet on a given star. So when you talk about a hot Jupiter, it's a few percent chance. So in a sense, the fact that hot Jupiter started to be detected when people started to look about thousands of stars, it's not just random, because it has to happen. The chance of the transit being 10%, well, actually, when you have 1,000 stars that you look for transit, you find one hot Jupiter. So that makes sense. We had 130 stars, 142 stars when we started the survey with Michel. Actually, we had 2 hot Jupiter in the sample that was observed. Now, what is quite surprising with this picture is the number of this group of planets that usually bear this kind of funny name like a super Earth or mini Neptune. So it's just massively dominant into the population of the planet we have in the galaxy. So it doesn't mean that the system, they don't have planets like the Earth further out, but at least we know that they are really a very compact series, most of them being by groups, and not only have one planet, they are really a series of planets together here. And when you think about that, reflect about that, it's as if you would fill in the orbit closer to Mercury. So in a sense, going back to the formation of planet, we have a serious problem here. We have a serious problem to understand the system, or you can see it in the reverse way. We have a serious problem to understand the solar system. So why the solar system is what it is? Well, maybe it's what it is because we are here having a conversation and because it had Nobel life. But that's another more philosophical discussion here, which is the perspective aspect there. No, this is a situation we are in, and that's a fascinating situation. It's also very frustrating situations, because we're very eager to connect the dots. So in a sense, we're missing completely the missing link here. It's difficult to value the likelihood of the solar system until we have been able to detect them. But progress is happening. Transit is pushing in that directions. There is a massive progress in the radial velocity, which is hitting a kind of a floor, which is related to the stellar activity here, but progress is being made. New instruments are being set up. And I'm pretty sure that there is no fundamental law of physics you break here. It's just more difficult than we thought. But that's what it is. But still, it's still a gift, because we have so much planet on short period, and then we are left to understand what they are. Well, this mini Neptune and the super Earth planet in particular are quite puzzling because when you connect the mass and the size, and I'm pretty sure you will discuss that during this meeting, you have these distributions of mass and radius giving you the bulk density, which is kind of understood for the giant planet when you think about Jupiter and Saturn, with the exclusion that most of the hot Jupiter they're sitting above, which means they are all inflated. Well, in fact, the fact that hot Jupiter makes it suspicious, and certainly one of the reasons why it's inflated, but I don't think there is a good theory right now that explains that, or there is a couple of ideas, but certainly not which is clearly setting up. What is fascinating is when you go down on this into this mass radius diagram, assuming this giant planet is essentially a planet of hydrogen with a small core, you don't make up a Neptune or Uranus there. Well, we know why, because they never managed to collect all the light gas like the hydrogen. And they are just denser. They have more heavy gas that tend to be icy. That's what they call ice giants. And they're sitting in a regime which is not really super filled when you think about all these many other planets we have in the mass range. But when you try to understand this regime here of the mass range or the radius range, everything becomes confusing when you get to Neptune and below. To help us, we can set the rocky planet boundary conditions here. That will be the green line, which is what you expect for the Earth. And then this blue line, just to give you an idea, if you imagine a water planet made of water, which is not really realistic here, but to give you an idea what it fills in. And then there's a very, very complex structure there with the famous Fulton gaps, and then possibly different origins for the planet, depending if they sit on a high mass range, like a Neptune mass, or on a sub-Neptune, or mini Earth, and all this kind of discussion you can have here about this. So we are into a fascinating world, because essentially between Uranus and Neptune, we have that side, and between the Earth, we have nothing. So all this planet there, we don't know what they are, which is an extraordinary territory for exploration right now. And that's one of this additional gift that can certainly a good piece of activity is going on along that line. Now, the fact we have this transiting planet is because we have so many planets in short periods, which, by the way, is a bias, but it's also an extraordinary opportunity. And we have to admit that this is pretty great to have transit configurations, because you can get atmosphere of planet. But again, I think what people start to understand, it's not that easy as it looks like. The principle is simple, but the practicality can be harder than we think. And for just the sake of the introductions, I would like to just identify a couple of elements that I think identify why it's not that easy that we think. Well, first, this is one of these beautiful early transiting configurations that has been measured from space. When you see the transit, the time when the planet goes in front, and so the time when the planet is behind, which is a secondary eclipse. What I like very much in this diagram is when you zoom in, you reflect about where comes the energy you receive on your detector. And essentially, you have the time here, and this secondary eclipse gives you the amount of stellar light that is reaching your detector. Here we're talking with a very big planet on short period, which means we have a quite significant amount of energy which is coming from the planet compared to the one with the star. But still, look at the number here. I think essentially 99.9% of the light you get in your detector doesn't come from the planet, come from the star, right? When you do that, in any case, whatever you do, you're massively dominated by the light of the stars. We should not forget that. I think it's like a bit magical. We can get the transit and the atmosphere of planet, but whatever we do, what the data is giving us is a lot of the stars, a little bit of the planet. Well, still, if you observe this secondary eclipse, you have this beautiful 0 point, and you can assume, if you assume, or you have to assume, that the amount of light of the star will remain the same, and then you can find out that the rest of the light that you measure is related to the planet, and gives this amazing discovery here of the dark side and the bright side of the planet. And from that, if you have wavelength, you can even compute some speed, some light, some motions on the atmosphere. It's quite amazing what you can do that. But still, I would like to just remind you, whatever we do, we're still dealing with a lot of light from the stars, and that's something that it can become a problem at the end. Now, we all know that transit is great, because transit gives you the size of the planet, but depending on the light crosses, depending if they are clouds, whether they are atmosphere, depending if there are some absorption of the atmosphere, you have a different size of the planet That is what we call atmospheric, transiting atmospheric measurements there. Now here we have experienced quite a lot of results recently, and certainly even more to come. And I would like to give you my share of thoughts about this, and I'm sure this will be discussed here. Well, I think there is really two categories of discovery here, and we should really be careful, where we're talking about that. Well, first, when you have a machinery like the Webb Space Telescope, and you observe a transiting hot Jupiter, like WASP-39b, what is extraordinary is you detect a signal of the transit which is significant, which is 2%. I mean, it's a very big Jupiter. I told you they inflated, so it helps in that case. And what you do see is there are clearly a change of the size. I mean, you see that on the data. You don't have to have a model to see that. You clearly have an increase of size or decrease of the size. So peaks and troughs, and you can identify clear, expansions of the planet. Look at the planet here and look at 4 microns. So actually you're dominated by the carbon dioxide, which makes the planet significantly larger than when you look in the 1 micron, when you're more dominated by the water, and you do see a little bit. So whatever is the techniques here you're talking, everybody will say, oh yeah, it's obvious you detect atmosphere of planet. And you don't need to talk about retrieval or any forward analysis there. Well, things become very difficult when you you move down to a world which is going to the Neptune or sub-Neptune, which is here the case of K218b. I just mentioned this one because he went to the press, and you may have seen that with the claim of detection of life on that planet. Well, when you move down to that kind of object, it's not 2% you get here, it's 0.2%. So pay attention to the change here of the scale. So of course the data are great, the same quality on the other data, but then the orb are much more dominating the structure. So the retrieval of this data, the analysis, it's hard, because depending on what you do, and the more noisy the data, if you do Bayesian analysis, you all know the tricks, and you essentially find, I think, what you put in at the end as the maximum solution. So the prior is essentially what you get at the end if you just guess too much. So we clearly see the challenge here that we are facing. Well, it's a beautiful technology, but it still is a challenging. And the fact that transit lasts for just a couple of hours does not make your life easier because you don't have that much data to capture. Well, thanks God we have these beautiful telescopes to do the work, but I think they would be a very active field, and I expect quite substantial number of discussions in the future about that. But please, when you start talking about that, we should clearly distinguish these two different cases, because on one hand, it's pretty obvious, like having a spectra of a star, essentially. The other one is really digging out something from the background, well, assuming that you don't have trouble with the star as well, because remember, whatever you do here, the rest of the amount of energy comes from the star. So if you get 0.3%, it means you have 99.7% that is really from the star there. Okay, so of course, the tricks, people are moving to a small star, so it's clear that small star helps, because then the transit is a differential measurements between the stars and the planet. So moving to small star helps, but, and I would like also here to draw some thoughts about, well, let's say that there has been a lot of enthusiasm for M stars, and for good reason, and they are amazing systems, like this one, for example, the TRAPPIST system. I take it because it's the most extreme system, and you have certainly less extreme system. But when you do these systems, when we translate this into the habitable zone, which is the case here, I think whatever we do, it's nice to think a system with the habitable zone, like the TRAPPIST system, but at the end, what we really have to remind ourselves, the system is not like that at all. The system is very compact and very close to the stars. And we have to admit that M stars, we don't know very much. M stars were seen as the most boring stars you can imagine, and essentially nobody would observe M stars for a long time. The core of the action for stellar astrophysics were essentially the big stars, because that's the one that makes supernovas and feeding the galaxies and produce all the chemistry in the galaxy. So a lot of studies has been done on M stars, but actually on big stars, on large stars, short-lived, but actually not very much on M stars. So M stars is kind of can unknown territories right now, but because of these discoveries of planet, and because of the fact we can detect small planet easier, and certainly we can do easy measurements of atmosphere of planet on this object, then there is a revival of the activity. But we should really be cautious here, because a lot of people have been claiming in a very optimistic way that they would have atmosphere and they would have this. But practically, when you think about the radiations and the length of the activity of the radiation, M-star takes so long to, cool down compared to G stars. So it's still an open question right now whether there is any chance that you have any atmosphere left on any of this planet just by the nature of the radiation from the star. So it's also interesting to see the community has a bit changed gear here. This very, very enthusiastic move for M-star that happened about 15 years ago, it's kind of refocusing a little bit, and people start to ask themselves whether they're really making good use of the data according to little knowledge we have on M-stars. Now, of course, I'm moving to M-stars, I'm moving to habitable zones, so it was mentioned earlier on by Chas. I think what has changed entirely during these 30 years is we're not embarrassed anymore to mention the word life. 30 years ago, we were seen as an alien. Not punt, assume here, talking about that. Practically detecting life right now, it becomes part of the game. And when you start having planet that is in the size of rocky world, you start detecting atmosphere, you start having habitable zone, it made absolutely sense to start talking about life. So I would like to just share some thoughts about detecting life, what I think is happening and what I think may be the future there, may possibly the challenge there. Well, to pay tribute first to the name of the meeting, which is second workshop, I would like to use this famous picture that was inspired and pushed very strongly by Carl Sagan. So this is a blue dot picture. You all have recognized it, I guess. Now, the reason why I show that is because there is a high expectation that we will do exactly the same, but not with a spacecraft in the solar system pointing to the Earth, but possibly with a spacecraft or even of a space telescope, ground-based big telescopes looking at a planet orbiting another star. So the reason why we want to do that is people have in mind this spectroscopic signature that you would have if you are able to measure the direct emission from a planet like the Earth. In this case, you have to go in infrared because this is where most of the energy is being produced by planet Earth. No, I don't think this is completely extravagant to talk about that right now. There's a good reason for that because one telescope has been designed for the beginning with the possibility to do that. This kind of an opportunity is this one. So the ELT, and I was part of the study team, I know exactly what happened in the early game. People were arguing to have the telescope smaller at that time to go faster because there were this idea of a racing against the other telescope. And the community stand very firm to say, no, we don't care to be the first. We care to have the telescope that at least will be able to try to do that. And there is a minimum size for the telescope, which is 40 meters to do that. So that was really the idea why it took so long and it was so complicated to do the DLT. It turned out to have 39 meters. But really, this is really the idea. So I think there is a possibility. Well, the number of stars that this telescope could do and detect directly planet, maybe limited to one. We're talking about Proxima here. But still, I think it's great to see that I think it was part of the motivation and requirement that has been accepted. So for me, what was beautiful in the fact that they moved forward with this telescope with that side, they accepted the principle. It would make sense to be the telescope that could go in that direction later on. That was a really big change compared to the early days of exoplanet discoveries. Now, when you start talking about detection of planets and which is atmosphere and detecting life, you are assuming a rocky planet, and there, whatever you do, we have to go back to the basis, and the only basis we have really to solidly ground any discovery there is the Earth. And I would like you to bring back some of the obvious facts for those of you that may be not familiar with that. Well, if you go to talk to planetary scientists, they have a very nice story about the history of the Earth. And that goes like a clock, if you are still using a clock with needle here, starting at 6 o'clock, going from a fully astrophysical element, which is moment, which is key for the formation of the planet, because at that time you get what you get. So if you're talking about chemistry, structure of the planet, the fact you make a planet at the given specific location into the protoplanetary disk matters. And that is why I think this nebular phase is critical to design what is actually the planet made. And you can then look at, for example, Venus and the Earth. And the reason why they are so different, why they have more the same mass and same size, it's possibly related to some very critical element at the beginning, namely the fact that possibly Venus never had enough water and maybe never had water, while the Earth had plenty enough water that survived so long. Now, the other element that's interesting in this continued formation of the planet is the fact the planet receives a lot of material. The delivery is massive, and that's cool, it's good, because most of the carbon actually is sitting outside, in the outside part of the disk, for the reason I was mentioning before. We have all this CO gas that tend to be in solid forms, and they are all falling asteroids, comets early on, and this is possibly the reason why there is so much carbon on planet Earth, not missing carbon. So very naturally, after 1 billion years, you end up with a carbon-dominated CO2, SO2 atmosphere with a lot of water that was there from the very beginning. And that's what we expect for a planet. So if you're asking me what I expect when I'm looking for a planet like the Earth, this is what I would expect, that kind of atmosphere. And that would be just amazing already to demonstrate that, because right now, this nice story I'm giving you, the evidence for that on Earth is marginal, because we have so few rocks that survive since so long. Essentially, all the rocks has been transformed, they're subducted, they're brought back to the inside of the Earth and just been expelled. The chemistry has been expelled back into the volcanic activity. So the early billion years, which is a very critical moment when you already get the conditions for that are called prebiotics, we know very little. So without talking about life, talking about detecting planet in that stage would be a fascinating moment for which astrophysics should really think seriously. No, we know what happened. So the condition for life were good in a way that the prebiotic activity developed life, and it had to happen very quick because the conditions on Earth changed pretty quick. I mean, we know the kind of a typical time scale. If you go for geophysical time scale is 10,000 years. So after 10, 20,000 years, the conditions are changing. You may lose the water, you may be dry, you may change the temperature, you may be icy. So whatever you do, whatever you form a kind of life, it has to be very quick. Maybe it has to be tried many times and failed many times, and at some point one survived and survive all this change of conditions and gradually change the complete structure of the atmosphere until getting the atmosphere we are right now. So we all know that kind of studies that I show on the right, and has been projections from early report about direct detection of planet, what it looks like in terms of reflection. So the albedo you see here. The reason why I show that is not to convince you about exactly what we should be detecting, but is to show you that it's not about detecting a detail. I think there is a massive difference due to the nature of the atmosphere and the absorption in the atmosphere between these different phases, depending when you look in the Archean Earth and the early before life or early life or late life. It's just massive. So the challenge is not getting very, very precise measurements, is to detect something. So the challenge is to reach detection level. So there that you reach detection level, even if you get a simultaneous observation of 10, you have it here. But it's a long way to go in that direction. But that's the hope. So I really hope one day we should be able to observe hundreds of stars with planet that maybe not exactly like the Earth, but in a similar way than the Earth, and try to do that. Now, what is good to remind as well, in parallel, there has been significant progress on life as we know it. It's called the prebiotic scenarios. We all know the famous Miller-Urey experiment that we know were not really applicable because the amounts of the energy you need in the atmosphere, it's called highly reduced. It's not applicable to the early Earth, but it's possibly could happen on a short time if you have massive comet impact. So possibly it plays a role. There is not a great enthusiasm right now for the hydrothermal vents for the simple reason that actually dilution is a serious problem, and there is no even any chemistry that it seems to work there. It's just by comparison. It's just the energetic of the reaction as being used as an element here, but not really the full development. So the most likely, I mean, progress, and the one when we've seen a lot of paper more recently, it's what's called the cyanosulfidic chemistry, HCN. HCN is a magic molecules. You have it in comet. It's extremely energized, and whatever you do when you want to make life, you better start at the high energy. So chemistry is about going down the slope of the energy. You start very high, you go down, and you make the complexity through that. So there's a couple of very complex chemistry planetary scenario right now which is being developed, has been I mean, everything has changed in the last 5 years on that. And the good news is if you study the planetary atmosphere and the atmosphere or the possible structure of a planet, you can reflect on this scenario. So it's a very interesting element to consider here. I was asked to give a bit of a look forward. So to me, the way I would see, I think, development of this field, well, I think whatever we like or not, we have to address the frustrating lack of solar system perspective. We need to find a Venus, Earth, Mars configurations. We need to detect the systems. It's difficult to compare the planet without them, and it's absolutely essential if you want to promote the origin and prevalence of life in the universe, because that the only life we understand is the one we know it right now. So we really need planet which can be compared, at least not being too extreme there. I think there is a way to make progress. I do believe radial velocity has still a future in that direction and can detect objects and combine with maybe space missions a bit later. No, a very important point for this assembly, small planets are not a topic for astrophysicists. It's the geophysics objects. And whatever you like it, you have to deal with geophysical dynamics, delivery, erosions, and surface chemistry, and possibly life. So it's not something you do usually in astrophysics. It's something we're not familiar with. So if you're really serious into this business, you have to consider moving in that direction, because this is all pieces of information which is essentially are sitting in books, which is essentially usually more read by geophysicists than astronomers. Now, if you want to stick on transit and you want to measure atmosphere, we have to face the reality. A transit of an atmosphere, it's measurements of 1%. Atmosphere is typically 1%. 60 kilometers, the atmosphere of the Earth, 6,000 kilometers. So 1% is about what you want to detect. So if you have a 1% transit and you want to find the atmosphere, it's 1% of 1%. 10 to minus 4, this is why you get this beautiful James Webb Space Telescope discovery, because this is typically where you get Galaxy 100 with the James Webb Space Telescopes and the great discovery. When you move to Neptune, you have a scale down a factor 10, then it's 10 to minus 5. Then you enter with this kind of challenging regime when you can do something, but it becomes very difficult. It's still within the James Webb Space Telescope class, but it's very, very challenging. Forgot about the Earth. It's 10 times smaller. There is no way I think we can observe Earth. Now, of course, we can trick the system, change a star. You take a star 10 times smaller and you scale up everything, and then you can observe Earth in the same way you observe a Neptune, and then you end into the 10 to the minus 5. So this is really what is going to happen in the future. So I think transits are great, but whatever we like it or not, we should really move to another world here, which is, I think, direct imaging. Direct imaging, that's the only way to make serious progress in the future. We should explore as we can from transit, but we will have to go for direct imaging. And then we know the numbers. If you go in the infrared, it's 10 to the minus 6. If you go in the visible, it's 10 to the minus 10. That's what you're tooling with. So we need a serious thinking. We need maybe a new community. We need a converging visions. I don't think this exists yet. I know there is a couple of projects there that will be discussed, but this is really the big challenges. My view of that, which I stole from one of my colleagues, this is what you may expect. So there is no way we can go into the small planet right now with the class of telescope we're having right now. We need maybe a 30, 40 class of telescope. There will be some Earth-sized exoplanet detected and measured with atmosphere, possibly. But if you really want to observe a dozen of them, you need a complete new generation. So there is a series of flagship missions and ideas that is being developed here. And I think this is great. Now, my last words, because I see I've still got 1 minute left, is if you want to make progress, I think it's time to leave the comfort zone. Again, this is not astrophysics anymore. This is a combination of a lot of expertise I'm talking here. So this is why I'm promoting since about 10 years. I'm not the only one. The idea of joining teams to combine expertise. It's a bit this idea of this last slide here. We need to fix a lot of problems. We cannot deal only from the astrophysics perspective. It has to be combined with the co-evolutions and the diversity of dynamic of the system. It has to be combined with the chemistries of life and chemistry of the planet to be able to decouple the chemistry of the planet from the possible chemistry that come from additional elements like life. And of course, we have to deal with a lot of practical problems, communication across disciplines, jargons, and trying to be careful about preconceptions. The fact that we are we have life on a system which essentially have no counterpart right now, I think is puzzling. It's very annoying right now. And I hope that in the next 30 years, and this will be addressed, and we will be laughing about the early days of exoplanet discovery with plenty of other systems that look much more like the solar system as we know it. Well, thank you very much. I think I'm right on time. Thank you.
Thank you, Didier. Thank you so much. All right, we have time for questions. We have plenty of time for questions. So in the room, we have two microphones here. If you can come down and ask questions. While people are doing that, do we want to start with a question online? Do we have any questions? Tracy, Catherine? Oh, okay, we can start with Chaz.
Hey, Didier, it's Chaz. Thanks very much for a very interesting and provocative talk. I love still seeing TPFI and TPFC on the graphs. You know, it's a 10 to the minus 6 problem in the mid-infrared, so I'm hoping Europe will pursue the LIFE mission while the US pursues the coronagraph mission, and of course, we expect that that'll be collaborative in both directions. I just wanted to get down into a bit more detail about where you see the radial velocity technique going with your Terra Hunter experiment, to the extent that you think you can push through the stellar noise problem to actually get us at least a few solid targets. Because I think the importance of having masses and orbits before we launch these flagships is going to be very important.
Okay, well, thank you for the question. Maybe I will keep being provocative here. I do claim that the only way to detect a nearby planet like the Earth or similar to the Earth the next 10 years is the radial velocity techniques. There is no other techniques right now. Well, it doesn't mean that we don't develop the others. Have you seen? I'm very strongly advocating for pushing for new hardware, new technology. But if you really want to find out around us, of course, you can then do the statistics with microlensing, you can do a lot of different activities, but this is really what I wanted to do. So what is the locking mechanism right now in radial velocity? Well, essentially, we are, in terms of technology, there is one missing element, which kind of work, but not really work, is the kind of reference, absolute reference. So we have the laser frequency cone technology, which is kind there, but not completely working to satisfaction right now. So if you look about the instrument that are using it, they're not using it completely or partially, but when you use it, there is plenty of example, and it's valid for any equipment. It doesn't depend very much of the kind of spectrograph as far as the spectrograph, which is fiber fed and stabilized. You get to the accuracy you need with the equipment if you have this. Now, I think in terms of technology, this is solved. Now, the other problem you have is the fact that the star is clearly variable in the submeter. Now, practically, the variability of the star is not exactly the same from what you expect from the Doppler signal from a planet. But because it's so much embedded, it's clearly not something you can do partially. You have to get focused and you have to plan in for the beginning. And most of the people believe that one way out of that is to have a systematic, a continuous measurements of the radial velocity of a star for at least a couple of years and ideally for 10 years. So essentially you measure the star every night as much as you can for 10 years. You do that because from one night to another one, the stellar variability is marginal. It's a bit like the weather. The weather doesn't change that fast, and you can essentially predict the change of the weather. If you combine that with other element that is helpful to identify possible change like proxies related to the activity, at the end, there is a serious hope that you will be able to deal with that. So that's the idea of terra hunting. Now, of course, the price to pay is you cannot do that on big telescopes because you essentially need to hijack the telescope for you. So I'm pushing right now to stop building spectrograph, very, very good spectrograph, stabilized, fiber fed, and expensive for big telescopes, but try to do exactly the same on a medium-sized telescopes because your 2-meter class telescope is plenty enough to do that, 2 or 3 meter telescope. Now, this is happening. There's Terrainding, there is another project. And the reason why you need to do that, because you can observe only 20 stars a night, 20 or 30 stars a night, and you need to observe the star for 6 months. So at the end, if you want to observe 1,000 stars, you need 20 telescopes. So this is the reason why I do believe there is a hope to identify all the nearby targets, preventing you have enough of this equipment. So I'm a strong believer that Terrainding will demonstrate that, and people will start embarking into developing this. The cosmology program, they have no problem building network of telescopes doing that. But us in our field, we have a little bit of challenge here to missing the capability to build up this kind of a community spirit that would develop a network to do that. It's possibly going to happen with the new generations. My role will be to demonstrate it works, and I will leave it to the next generation to build this network. But that will work, I'm pretty sure.
Okay, thanks very much, Didier.
Thank you. Okay, we have a question online.
Yeah.
Tracy.
So we have a question online asking, what does it take for a potential exoplanet discovery to become a confirmed one?
Well, sorry, I'm not sure I understand really the question. To become a confirmed one? What? Okay.
I guess it's just like what it takes to confirm a potential exoplanet candidate.
Well, there are 6,000 planets that people consider as being detected. So I know there is not anymore any discussions about the detection of a planet, except in some rare cases, because we have so many examples we can refer to. So for the techniques which people have been using so far, I think it's pretty clear what needs to be done. No, if it's about the cost of telescope time, I don't know exactly what is the question. No, for the new technology that will come, like microlensing, there will be a bit more work, because here we're lacking a bit of background, but it's very likely that there will be whole populations of planet discoveries that will bring a lot of statistical information in the future, and they will have to redefine maybe what are the minimum criteria that people should agree to consider the planet has been detected, because microlensing, you just do it once and then it disappears after. But for most of the planet being detected, I don't think this is a serious topic of discussion. If I understood right your questions, maybe I misunderstood your question.
Okay, I think you got it. Or at least we think you got it. Okay, we have just a couple more minutes. So next question in the room here.
Yes. Hello, Didier. I really appreciate your discussion. I wanted to ask, this has to do with measurement uncertainty. And you talked about how 99 point blah, blah, blah percent of the light, looking at an exoplanet has to be filtered. I guess this has to be filtered out in order for us to get a measurement of the gases that we get. So how does that affect the uncertainty of the actual results? And do we have to take, how many orbits, how many transits do you have to take over time to reduce that uncertainty? And does that reduce the uncertainty? Do you take an average? How does that go?
Well, I think the systematics and biases and interpretations of the transit discoveries is a whole topic by itself. Again, it depends a bit of what exactly you observe. So there is a series of challenges that people have to be confronted with and have been confronted in the past. The first one is, do you have the synchronous ratio needed to make the detections? Because of this, because 99.9% of the photon come from the stars, so you need to have such a high synchronous ratios to be able to be in the conditions to at least assume it's just a shot noise to get rid of that one. Now, the second one is, can you maintain the stability of your equipment when you do your measurements? And it has been a lengthy discussions in some of the case of claim of change of the signal has been made. And especially most of these technology are not being designed to do that. The only telescope that will be designed is Ariel, that has this capability. All the other, they have been tricked. James Webb's telescope was never thought for Exoplanet. At the time it was designed, it was to do cosmology only, and they kind of reshuffled it and redesigned part of it to make sure they could observe. And right now, I think 25% of the time is being used for this. So that is really the second element. And then the most challenging one is you have to deal with this kind of a complex signal And the planetary atmospheres depend of a series of elements, which one of them is the temperature pressure profile, and you have to guess this, and depending if you have an aversion or not. And the other one is you have to play with the conditions you have and diversity of the component you have in the atmosphere and the thermal regime you have to deal with. Now, there may be some let's say some cases where there are different options, and you may get exactly the same results if you are dealing with low synchrotronous ratio. So at the end, it's all about if you get a very high synchrotronous ratio, it will be obvious. Systematics can be lowered down to a level you feel confident with, and then you have the discoveries. And I think for all the analysis being made these days for the giant planets, I think they're really amazing. Now, when you start going down to the mini Neptunes, I think we will see a lot of claim and counterclaim and change and refocus there. And it's maybe why there has been quite a significant number of them being observed since the launch of James Webb Space Telescopes, but not so many papers out because it's difficult. So you're right, you're pointing your finger on suddenly on the most difficult aspect right now of the business of exploiting all this planetary atmosphere, which is dealing with this kind of data that we're not used to. But again, progress will be made, like always. And I'm very eager to see what's going to happen in the next 5 years, because people will get used and more familiar with that. And there will still be a threshold somewhere, and there will still be mistakes being made, which is part of the science. And it's a good topic for workshops.
All right. Thank you so much, Didier. Let's everybody give Didier a round of applause again.
Thank you very much. Enjoy your meeting.
So we did have another question in the room and more questions online. So Didier, I don't know if you're in the Slack workspace or not, but if you're not, then we'll work to get you the question somehow. But if you can join, that would be great, because there are more questions for you
I have
there.
a look at the Slack. I have a look at the Slack. Yeah.
You look at the Slack. Awesome. Okay. And so, yeah, Stuart, you can put your question there, and yeah. Yeah. Okay. So we have a break now. We're supposed to, according to the schedule, we're supposed to come back at 10:10, but that's only in 13 minutes. So I'm gonna, we're gonna come back at 10 past to give everybody 25 minutes. So, and do we have the bell? Do you guys have the bell? I don't know if you have the bell. Okay. Anyway, come back, be in the room by 10:10 so we can start again. We have a really great panel coming up. Thanks, everybody.
Thanks, Didier.